This is a relatively short talk that describes MLOps. So first, the definition. Machine learning operations is the set of practices that automates and manages the process of developing, deploying, and maintaining machine learning models in production. Contrast that to the definition of DevOps, which is almost the same, except that it is not talking about machine learning models, but it's talking about software. So let's talk about the stages of MLOps. And what we see are that there are 6 stages. Data preparation and engineering. So first of all, you have to collect and clean the data, the raw data, and transform it into a usable format. And you need to maintain version control over the various data items and use something called feature stores to enable you to define which portions of the data are most useful in model prediction. So if you look at the data curation pipeline, if you can read this, you start with raw data, and then each step is the data is labeled. It's then classified, and it's formatted so that the model has some consistency in formatting, and this takes people. Okay, you can do it automatically, but it usually some people will need to verify that the formatting and the data is done correctly, and there are tools which we'll talk about to assist you in doing that. And now you need to verify the data. So you have a data set, and you want to make sure that the data is objective. So you don't want to have built-in biases for the data, discrimination, and so on. You want to make sure that the data that you have reflects the use cases that you're going to use for the model. And I'll repeat this, but an example is housing price data. You collect data for housing prices in a particular urban area. If you try and apply that to a rural area, then it's more than likely not going to be correct, because there are different forces that affect prices in rural areas than they do in urban areas. You don't want to make any assumptions about individuals. You do not have antagonistic AI, so it's possible to put data in that allows various types of attacks, and you don't want to have that. And that's all part of the verification phase. And again, there are both human inspections of the data and machine inspections of the data. And you might set parameters with automatic checking to assure that the points above are done. So there are tools to support this. And this lets you do what's called shift left testing, which finds issues in the data before its use. So again, you want to find things as soon as possible so that it doesn't go into production, after which you may have erroneous results, which you need to deal with if you can catch it in the essentially the requirement stage. Then you don't have the same set of problems. Now, given that the data is done and labeled, now you want to choose a algorithm to base the model on. So there are different kinds of algorithms. There are different algorithms per se, and they will give different results. And some are more accurate than others. Some are more expensive than others. And data scientists, and machine learning engineers will try different algorithms. And there are things called hyperparameters, which are parameters of the model, not parameters applying to the data. So for example, I may want to fit a polynomial to a set of data. A hyperparameter, is this a quadratic? Is this linear? Is this a quadratic? Is it a cubic? Is it a higher order? That's a hyperparameter because it defines the kind of model that I want to work with. Then I want to test it. So there are two stages to that testing. There's the validation stage, which essentially is finding the right hyperparameters, tuning something for hyperparameters. And then there's the testing stage, and the testing stage is the place where the model is applied to data that was not used in the training. So there's a training set, a set of data that you use to find the parameters of the model, not the hyperparameters, but the parameters. So for example, if I want to fit a linear a line through a set of data, then the line is defined by a slope and an intercept. Those are the two parameters of the line. And I would then say, okay, I've defined this line through a set of data. Now let me apply it to data that I wasn't used in, and that would be the training phase. And now let me apply it to data that was not in the training phase. That's the testing thing. So validation it works with hyperparameters. Testing works with data. Once you've decided on the model, testing works with data that you haven't seen before. And there's a pipeline again that deals with this. So it builds a model, it implements the code. So there are libraries that have model implementation code, so you don't have to code it yourself. You can, of course, but typically you would use a library. Then you train it with a set of data. Then you test to see that you have the right model, which is the hyperparameter. And then you test to see that that's the validation phase. And then you test to see that it is correct with respect to the data that is not been used for the training. And again, there are people involved in this process just to verify the results, and there are tools involved in this process. And in general, this process of building a machine learning model is both tool and personnel intensive. Once you develop the model, then you deploy it and you serve it. So serving means that I am going to give it real data and and use the output. So you have to package it, and then you deploy it into a production environment. And this packaging depends on the complexity of the model and the number of parameters and so on. Typically, it's packaged as a container, and then it's treated in the deployment process as any other container. So a container can come from the model development, or a container can come from developing a container through code, one way or another. And those are both treated the same, and they are deployed. And you deploy a container into a container runtime, and it manages things like scaling and discovery and so on. And this is the picture of the pipeline. And again, the models are intended to be used in the real world. They're packaged into some sort of deployable artifact. And again, depending on the complexity of the model, that's a container. And you may need a pipeline that will enable you to curate the data. So we talked about that before. And you would test in operational environments during the testing phase. And this provides methods for data injection and prediction and so on. Again, if you use the example of linear regression, it's characterized by two parameters. That's it. Okay, so you train it with a variety of model with data. You use it on a variety of data, but the actual coding itself and the model itself is actually very compact. And this will happen quite frequently, that the training data may be voluminous, but the actual model that results, depending on the type of model that you choose, of course, uh, can be very compact and packaged fairly easily. Once you've built and deployed it, then you execute it, and you need to monitor it to see that it provides reasonable accuracy, reasonable latency, and there's a phenomenon called model drift, which means that for some reason or another, the data that you trained the model on is no longer representative of the real world. Again, to use the housing example, housing prices go up and they rarely go down, but they do. And that would be considered model drift. And so you would have to retrain the model in order to capture the latest set of housing prices. And so you would monitor the output of the model on real data. And this can be done both in terms of comparing the output of the model to ground truth. So ground truth is what is really out there. So you look at a house that has a price, and you see if the model can predict that price or get close to that price. And if it does, then you're happy with its performance on that set of data, but not necessarily in general. So you need to monitor it and make sure that it doesn't that its predictions are respectable in some sense or another. It's also possible that you could attack a data set or a model, and that's a practice called adversarial AI. And there are ways of testing for that, and there are ways of generating adversarial AI. We won't go into that. And once it's been deployed, then you monitor it. And this is your operational model. And so each model prediction is validated in one way or another. And it possibly, if in fact the model has drifted, then it has to be retrained. And so you might trigger a retraining phase where new data is put in and the model is in fact retrained. And all these things are recorded. Okay, so we'll talk about tools in a minute, but in general, you need to know what you've done, what you predicted, what data you've changed. So part of the cleaning process might be to eliminate certain data because it was typed wrong or it was entered incorrectly or it was duplicate. And so you need to keep track of all that. And again, there are tools that let you do that. And personnel, again, are involved in the monitoring, can be involved in the monitoring. And throughout the life cycle, there are governance practices. And the practices ensure that the model is fair, transparent, and compliant with regulations. The number of regulations applied to AI systems is growing. And California has it's a matter of law. In the European Union, it's a matter of law. And you need to make sure that the models that you produce are compliant with whatever the law is in the locality where it's being used. Okay, so I mentioned several times that there are tools involved in this. These tools will track the experiments, they'll track the pipeline and versions, they'll track the workflow, the orchestration, they'll track the model deployment and service, and they'll monitor it. So there are tools that track experiments. So what's an experiment? Let me try this model. What does it do? How does it work? Okay, well, you want to track that so that you don't try it again. So it might be that after a while you'll come back and say, I like that, the third model that I tested, what was it? And so you need to have a history of the things that you've tested and what their parameters are and what the results of the running the model on the data were. So that's the experiment trade. And there are a couple tools. I mean, there are multiple tools in all of this that do that. You want to keep track of versions. Okay, so I changed this data item because, and then you give a reason. I think it was entered incorrectly, so I may delete it. It's an outlier, and it doesn't seem to fit with the other things, so I'm deleting it. I'm normalizing a collection of data so that they're comparable. I mean, there are things that you do, and you need to keep track of all the changes that you made and what versions of the data you have. And again, there are tools that allow you to do this. Your normal containerization platforms are used to monitor, to manage the containers and the models that are done. So there's nothing particular about that. Once you've served it, then you want to make sure that you that your predictions make sense. So you deploy it. You know when you deploy it that this particular container contains an ML model because the ML models are probabilistic, not deterministic. And so the answers they get may or may not be correct, and you want to monitor that type of activity. And in order to do that, you have to identify the fact that these are ML models and require special monitoring. And again, there are platforms to help you do that. And then anytime you have a tool chain or a pipeline, it's very nice if the first tool produces output that can be used as the input for the second tool, and so on and so forth, so that there is compatibility among the tools. And the cloud vendors and various types of other vendors will give you a suite of tools which cover the life cycle of the data and are all compatible with each other. And so here's an example of a ML implementation scenario. You have data, you package it, you build a tool, you build the model, you package it, you serve it, you monitor it. The workflow is done through something like Kubernetes, and you monitor it at the end, and presume possibly re-trigger the whole process. So what are some of the challenges of MLOps? And we'll identify 4 of them. So they rely on data, and data is constantly changing. So a model performance can degrade over time. I mentioned model drift, and that is because the data is not the correct data for the particular environment in which it's being used. It's not the correct data for the type of use that it has. It has some built-in biases that need to be corrected, and so on. So model drift is a concern. You can't necessarily reproduce things, and because the data has changed, the code has changed, or the environment has changed. Okay, so I developed this model on my laptop, and now I deploy it to the cloud, and it has different timing characteristics, which may result in different responses and different answers. Scaling is difficult, so manually managing many models, so I can have a whole suite of models. And these models, so think of a bank, and they have numerous machine learning models floating around, and they work on large data sets, and so you need tools again to manage this, and that's the difficulty. And then the other thing that happens is you're developing interdisciplinary teams. So there's a theory that actually dates from the 1950s that talks about teams, and teams are formed, then they storm, They fight with each other. What are we going to do? What words do we use? Who's in charge? There are issues involved in team formation. Uh, then there's the next step is norming, meaning that norms are adopted, and you decide within the team about which vocabulary you're going to use, which models, how you're going to do things. And then there's performing, that you actually can perform the work that the team is set out to do. And this takes time. And the more different disciplines you have, and the more people that you have in the team, the more difficult it is, and the longer that it takes. And that's a problem with machine learning, because inherently you have software engineers, you have machine learning engineers, you have data scientists, and the software engineers may in turn have different specialties. And so the notion of collaboration becomes complicated. And then finally, let's compare this to DevOps. So there are three different differences between DevOps and MLOps. One is the scope. What is included in DevOps? Software development. What is included in MLOps? It's models, data models, and it's machine learning systems. And so that's both the data collection, the experimentation, and the model retraining, in addition to doing the software. So you can think of this life cycle of a machine learning model, which we talked about in the beginning, and compare that to the life cycle of a software. And they're different. You have complexity. Okay, machine learning models, again, depending on the particular model that you choose, are more complex because their dependence on data and the choice of models that you do. So two different machine learning engineers may produce two different models for the same set of data, which might give you different predictions. And then again, I talked about the difficulty in terms of teams. So just to summarize, MLOps is DevOps plus data, plus model creation and management. And you can view it as 6 distinct stages, and each stage has a collection of tools. The model development and management introduces challenges because of its dependency on data, and the data may drift or not represent the current environment.